Today we're going to take a look at the idea of injective functions, surjective function, bijective functions, right? So let's take a look at definition A. Okay, definition A says that f is an injective function if for every element y in B there is at most one element x in A for which fx equals to y. So what does this mean? This means that every element in y can only have one corresponding element x, which I'll show in later example. This might sound confusing at first, but it's gonna get clear once you see the example. And that if f is a surjective function, it means that for every element y in B, there is at least one x in A for which f of x is equal to y. So this means that every element y in B must have a corresponding element x. It can have multiple, that's fine because that's satisfied the at least one definition. But in the injective case, it can only have one corresponding element x in domain A. Okay, so a bijective means is that if a function is bijective, if it's injective and surjective at the same time, so it satisfies two definitions. So let's take a look at an example that I drew right here. As you can see in our domain, which is let's say I'll call it domain domain A, domain B, and there's a function of with domain of A and codomain of B, right? So can you tell if this is injective or surjective? Well, the answer is neither, because as you can see, it doesn't satisfy the injective definition, because as you can see in the codomain B, right, the element G has both C and D as its corresponding X element in our domain, but one of our definitions says is that there is at most one X element X in domain A for which f of x equal to y, but here we have two, so it doesn't satisfy the injective function, so it's not injective, right? What about the surjective? What surjective says is that for every y in B, there is at least one x in A for which f of x equal to y. And is that the case? No, because as you can see in our codomain, H and I doesn't have a corresponding element x in its domain, right? So not every y or not every element in B has a corresponding element in A. So therefore that is not surjective. So it's neither surjective or injective. That's number one. And let's take a look at our number two. Well, on number two, we have A, B, C, D as usual, and we have E, F, G, H, and then there's an I that is not related to anything. So what is this? Pause the video and think about it. Well, this is in fact injective, because as you can see, every element in B has at most one corresponding element in A, right? But it's not surjective because there's an I isolated outside of not outside of, but it's inside of, I is inside of a codomain, so it is an element of our codomain, but it doesn't have a corresponding element X in our domain. So therefore, it's outside of it's like it doesn't have a corresponding element in X and X in A. So therefore, it's not surjective. So what surjective says essentially is that every B or every Y in our codomain B must have a corresponding A. In this case, it doesn't, but it's still injective because injective didn't say that we couldn't have a element like I that is not connected to any of them, right? It only says at most one. So it's injective because E, F, G, H are each correspond to A, B, C, D. So there's no situation as in the last case where like C and D both connect to G, each one just corresponding to one. So therefore this is injective but not surjective. Okay, let's take a look at our next example. Well, in this example, pause the video again and think about what is this. This is in fact surjective but not injective, for a very obvious reason. Well, it satisfies surjective function's definition because every element in the codomain has a corresponding element in our domain, right? So it's surjective. So every B in this case has an A. But it's not injective because as you can see, G is connected to C and D. In our injective function definition, if we recall, it says that there's at most one in X, there's at most one X in element element x in A for which fx equal to y. And here we have 2, which is C and D connected to G. So therefore it's not injective, but it is surjective because every B has some A. Every element in our codomain has some corresponding every element x in our domain, right? So it's surjective but not injective. So let's take a look at our last example. Our last example says that, well, you can see A, B, C, D are corresponding to E, F, G, H. Okay, so this is what? This is bijective. Why? Because it both satisfy the definition of an injective function and a surjective function. An injective function says is that, well, every element B, element Y in our codomain B here must has at most one corresponding X. In this case, it does, right? Because there's no situation where two of them are connected to one, right? There's no like B and C are connected to G, or C and D are connected to H. They each have their own connection. Each element in codomain has only one corresponding element in our domain, right? But it also, so it's injective, but it's also satisfied the definition of surjective, because surjective says that we must have that every element in our codomain must have at least one. And in this case it is, because there's no situation whereas, there's in this where, there's an I left out of there and that nothing correspond to it, right? Here that every element correspond to each other and it's also one to one, which is injective, right? So therefore it's both surjective and injective. So we conclude that this is a bijective function. So that's the definition of injective, surjective, and bijective. And in my next video, I'm going to show some example to algebraically prove that some function are injective or bijective, right? Or subjective, sorry. But yeah, so that's it for the introduction on this. But there's more example coming, and please subscribe if you feel like you learned something.